Hello and welcome to this virtual seminar on understanding powder stability through moisture sorption analysis. My name is Brady Carter and I'm a research scientist at Decagon Devices. And my hope today is to be able to provide some additional information about ways that you can utilize information provided by moisture sorption characteristics and water activity to be able to control the problems that exist in powders that affect their stability, and to make them have a longer shelf life. So when we talk about powder stability, there are several different degradative occurrences that can occur that would affect the stability of powder and can essentially end its shelf life, rendering it unusable for different purposes that it might be used for as an ingredient. A lot of different types of ingredients are in powder form, of course. One of those could be chemical stability. If there's some sort of a chemical reaction in the powder that causes it to lose its quality, that could possibly end its shelf life. It could be microbial stability, not a typical problem in powders, but there are situations that are rising now where we see where microorganisms are able to survive, although they don't proliferate or grow in powder types of products. The powder is then added to as an ingredient to some sort of a product that's at, say, a higher water activity. It's now in conditions where that microorganism starts growing again and it can proliferate to levels to cause infections. And so an increased emphasis on even the microbial stability, or at least the microbial quality of powders and efforts to try and sterilize even in the powder form. But one of probably the most typical occurrence that causes the end of the stability or shelf life of a powder has to do with its physical properties. And here we're talking about flow and caking and sticking, and these occurrences that just render that powder very difficult to work with. So let's talk a little bit about powder flow and caking. This is actually quite a complicated subject. There's a number of different methodologies that exist to try and investigate the flow properties, the caking properties of different types of powders. All of them with their benefits, and all of them with their downside as well. And not all of them provide the information that's necessarily needed for the particular application or use for a powder. But majority of the food powders, at least, are spray dried, and as such they exist in what we would call an amorphous or a glassy state, where as opposed to a crystalline type of state, although there are powders that are certainly used and added as ingredients in crystalline form. But a large number of them are in an amorphous state. And amorphous simply means that it's an unorganized condition. And when it's in a glassy state, that glassy state refers specifically to a condition of very low viscosity, very low free volume, very low mobility, and it results in a metastable condition, where as long as you maintain that glassy state with that powder, it will maintain its stability. It will maintain its flow properties. It won't get sticky. It won't cake. It will have a very extended shelf life. And this has been well established that the caking phenomenon that happens is very tightly related and controlled by the glass transition from a glassy metastable condition to what we call the rubbery state, characterized by a much higher mobility and a greater chance for particles to interact with each other, become sticky, and start to cake and clump. And certainly pore size and shape has an impact on the susceptibility of any given powder to the caking and clumping. If you manufacture a powder in different ways, and as a result you end up with different pore sizes from that process, then there is the opportunity for there to be differences in how those products respond and how they cake and clump. And when this process happens, what you see is a free flow powder is transformed into this agglomerate that becomes sticky and starts to cake up. And when you can have different consequences from that is shown in the illustration here. One is that you can have interruption of flow. So you have these caking, these sticking particles that they start to adhere to the sides of the hopper, and they possibly adhere to each other and create an arch, or they could create what's called a rat hole. And at that point, there's no more flow down through the hopper or through the piping where the powder is being transported as an ingredient into a process. So then you have a problem. You don't have any ingredients flowing. Your powder doesn't flow, and you've got to stop the process, stop the line, and try to figure out what's going on. And then, of course, you can have problems that come during processing, where you've got a lack of ingredient coming in the right amounts, and then all of a sudden it all just flows, and then you get a huge amount of it where you get too much coming in and you have to adjust the line. You may get segregation because during that caking and clumping process, particles that are finer will be able to move through the system, and then you end up with fine particles followed by more coarse particles. So this can really be problematic, obviously, for when you're trying to use powder as an ingredient. So if we take a look at the science of powder flow and caking, and we want to simplify it, and certainly it's not a simple process, but as with most things, as much as we can simplify it, we gain benefit from that because it makes it possible to more easily come up with some possible solutions to the problems that exist. And so really when you break it down, the three main factors that are influencing and affecting whether or not a powder is going to cake and clump are moisture, temperature, and time. And at a given condition of moisture and temperature, the time that it takes for problems to happen for caking and clumping are completely dictated by what that moisture is and what that temperature is. So if you know, it's possible to model all of this. If you know the moisture and temperature conditions that the sample's been exposed to, then it is possible to be able to figure out, do some rate calculations, figure out exactly how long it's going to be before a particular powder starts to cake and clump, with the understanding that that relationship between moisture, temperature, and time is going to be very specific to the material, as well as even to its pore size and particle size and so forth. So what are the typical approaches to try and deal with powder flow issues when they exist? One of the common things to do is to measure moisture content of powders and try to track that moisture content. We're going to talk a little bit about why that's not necessarily the most effective way of being able to impact the flow properties of powders. That there are better ways to track the moisture level that have a better correlation to the actual flow properties. Another is to package the powder in a high moisture barrier packaging to try and prevent moisture infusion into the powder, which will result and lead to caking and clumping. May store it at low temperatures, since again, keeping in mind the idea that it's moisture and temperature along with time that are the impact. So if you can store at low temperature, you could eliminate the temperature effect, but of course that can be costly as well to have special storage conditions. You might include some sort of a desiccant in the package with the powder material that preferentially takes up the moisture and keeps it away from the powders that would start to cake and clump. And you can do this also with anti-caking agents that have characteristics of being hygroscopic, but and being able to incorporate and bring in moisture without having subsequent large impacts on its water activity. Agglomeration is a process of creating larger particle sizes so that they won't be as susceptible to sticking and clumping up. And then there's just the old-fashioned get up and beat on the hopper, because you've got a plug up there because the powders start to cake and clump, and you got to get things flowing again. So there's some sophisticated and all the way to fairly simple solutions, none of them being very wonderful. But as we explore more into what actually leads to these degradative occurrences, hopefully we can provide a few other suggestions and ideas about how to be able to effectively control the flow properties of powders. Now just a little bit on why moisture content doesn't work as a way to be able to control flow. And one of the reasons is because moisture content in and of itself is just telling you how much water is present. and not necessarily what the water is doing or how available it is for plasticization, that can lead to glass transition, which then, of course, leads to caking and clumping. And so just from the very beginning, moisture content in and of itself is a very difficult measurement to get good repeatable results. It's fraught with a lot of difficulties, so that's one reason. It's hard to get good repeatable results that you can rely on. And there's no standard for measuring moisture content, which makes it difficult to know if you're actually getting the right value on a consistent manner. The other is that, as you can see visualized in the figure that appears on the right, these are moisture absorption isotherm curves for powders. And a moisture absorption curve has water activity on its x-axis and moisture content on its y-axis. So what it's showing is that relationship between moisture content and water activity. And you'll notice that for these powders that are shown here, they all initially have very flat isotherm curves. In that glassy state, they tend to be a fairly flat curve because in that metastable glassy condition, there's very little available sites for water to bind. Once it experiences a glass transition, you'll notice that they all experience this nice inflection, sharp inflection in the curve at that phase transition. But at those levels below that phase transition, where you need to keep the powders in terms of their water activity in order to keep them free-flowing, notice that relationship between water activity and moisture content is very flat. So you could see almost no change in moisture content, but get a huge change in water activity down in that low range. And if you weren't tracking water activity, only moisture content, you might not think that anything's going on or any reason to be of concern. But then you check water activity and you find out that you're getting very close to that critical point that we'll identify in just a little bit. And you would have never seen it with the moisture content spec or tracking moisture content, but you would be able to see it if you were tracking water activity. And so from that, and because of all of that, there are better correlations between water activity and caking. And a lot of that stems from the fact that there are better correlations between water activity and this glass transition or phase transition phenomenon. So let's spend a little time and compare and contrast moisture content and water activity. We've talked about moisture content not being the preferred way of being able to track powders and whether they're going to cake or clump. What is the difference between the two measurements? So moisture content is a quantitative measure of how much water is present in a system. 10%, 20% means that of the stuff that's present, 20% of that is water. And it can be on a total weight basis or it can be on a dry weight basis. And this is an extensive property that does depend on the amount of material. Water activity, on the other hand, is a measure of the energy status of water in a system. So this is a qualitative measurement instead of a quantitative measurement. And it's a measure of how much energy water has overall in a system. And we do that in comparison to what it would have if it had pure water. So as that energy of that water reduces and is lowered, then of course that water becomes less available for things to happen. It's not telling us just how much water is there with the moisture content. It's actually telling us what the water is doing and how it's behaving within the system. So a little bit more about water activity. Water activity is derived from fundamental principles of thermodynamics, from the second law of thermodynamics, that basically tells us that if you want to know something about the energy status of water or energy of water, then you need to look at what we call escaping tendency or fugacity. Because as water molecules have more energy, they have more of an ability, their energy is substantial enough for them to escape into the vapor phase. So if you put them in a sealed chamber, their water molecules are going to have enough energy to escape into the vapor phase. They aren't going to go anywhere. And over time, you're going to come to this state of equilibrium where there's no net change in the number of water molecules in the vapor state. At that point in time, the water vapor that's in the vapor, or the water molecules that are in the vapor state, are going to exert some sort of a pressure. And we call that vapor pressure. And that vapor pressure is going to be directly related to what the energy of the water is in the system. Because as the energy of the water increases, so will that vapor pressure, because there are more water molecules that can escape into the vapor phase. If we take that vapor pressure value and make it our numerator and divide it by what the vapor pressure would be if you were dealing with pure water, then you get a ratio. If the vapor pressures are the same, then the water activity is 1, which is an indication that the water in the system has the same energy as pure water. As the vapor pressure over your particular sample decreases away from what it is over water, then that ratio starts to decrease and the water activity goes down, 0.8, 0.7, 0.6, 0.5, and so forth. So it's giving us a relative idea of what the energy of the water is in a system in comparison to what it would be if you had pure water. And all this has to be done at a constant temperature. And then that provides us with this thing we call water activity. So we steer away from the old definitions of free and bound or available water and go and stay with this idea of the energy status of water. And the reason why we steer away from those free and available terms is because those don't have any scientific meaning established with them. They can mean different things to different people. When used in the context of energy of water, they do make some sense, because as the energy of water is reduced, it of course becomes less available, becomes more bound in the sense of chemical interactions that are causing its energy to be reduced. So they can be used in the correct context, but they mean different things in different situations. And so try to stay away from that using those old definitions and emphasize the fact that water activity is the energy status of water. And water activity is equal to equilibrium, is the same as equilibrium relative humidity just divided by 100. So if you measure the relative humidity inside of a sealed chamber and get an equilibrium relative humidity and divide that by 100, you would have water activity. Now let's talk a little bit about moisture content. Moisture content, being a quantitative measure of the amount of water, is a completely empirical measurement and relies on the measurement methodology itself, because there is no standard. There is no standard that you can take and put into a moisture content instrument, and from that know whether or not the moisture content instrument is giving you the right answer. It is possible to do that with water activity. You simply use a salt solution of a specific concentration or at saturation, and those water activities are known because they're determined or dictated by thermodynamics. So I can take a sample of a salt solution, put it in a water activity instrument, and beforehand know what the right answer is, and then determine whether the instrument provides that correct answer. That being the definition of accuracy, and whether or not you hit the bullseye or hit the right answer. Without a standard, then there's no way of knowing the bullseye, and there's no way of knowing whether or not the answer is right. So with moisture content, because there isn't that ability to have a standard and to be able to measure accuracy, it's not possible to report an accuracy for moisture content. Even though there's lots of reports out there for accuracy, the truth is there is no actual standard, because water in doesn't equal water out, and because on the moisture content scale there is no zero. There is no zero reference point that's scientifically defined as dry here on Earth. So it's impossible to be able to create a standard. So you have to just rely on whether or not the results are repeatable. And if you do get repeatable results, at least you know if something has changed. But in terms of a measurement, even though it's a fairly simple concept to think that 20% moisture content means that 20% of the sample is water, it's actually quite a difficult measurement to get good repeatable results. And essentially there are two primary methods for measuring moisture content. One is loss on drying, and this is dependent upon evaporation of water out of a sample through Fickian diffusion of water out. The sample itself dictates how long that takes and what temperature has to be achieved to be able to get the water out. As such, we use the term moisture content for a specific reason, because at elevated temperatures that we would use for a loss on drying, such as 100 degrees C, 120 degrees C, so forth, things other than just water can volatilize out of the sample. And hence we use the term moisture, meaning anything that volatilizes out at elevated temperatures, as opposed to it just being water that would come out. And so we don't use the term water content, we use the term moisture content. Now in an attempt to try and overcome those limitations, you could go to a titration method such as Carl Fisher, where it uses a reaction that involves water as one of the reactants to determine how much water is present. You continue the reaction until all the water is used up, in which case you'll start to get a buildup of the other reactants, particularly iodine, which then impacts the electrical properties of a solution, and you can track that by figuring out exactly how much iodine was used up to that end point, and then directly relate that to water. So that's a way of being able to try and specifically measure water content and not moisture content. But again, lots of challenges. You have to solubilize the water out. If you don't get it all out, then you won't detect it. So just like with a loss on drying, Carl Fisher will give you an answer. Whether or not it's the right answer is impossible to know. So with those challenges in mind, we've talked about that there isn't a standard. other things than water volatilizes. There's also lots of different methods, each one of which will give a little bit different answer as to what the moisture content is. So it's very difficult to get reproducibility, even more difficult to get reproducibility than necessarily the repeatability. When you try to match the results from different locations, it's very difficult. You can get ranges from anywhere from 8 to 18% moisture content for a particular product. And a lot of this has to do with there being many sources of variation, lab conditions, scale, the scale that's used, the temperature that's used, the person doing the weighing, spilling a little bit out of it. All of those can lead to a lack of repeatability and reproducibility. And then it's important to understand the reporting basis. Is it dry or is it wet? A lot of times those get used interchangeably or without any kind of information about what type of moisture content it is. People report it in different ways. And you can't compare a moisture content reported on a dry basis with one that's been reported on a wet basis. They don't directly compare to each other because they're being divided by different values. So to further illustrate this difference between water activity and moisture content, water activity being the energy, moisture content being the amount, we can take a look at a classical experiment where we would take, say, a cracker whose water activity initially or inherently is quite low at 0.3, a water activity, very stiff texture, a snap to that cracker, and its moisture content is very low at 4%. If I were to take that cracker and I put it inside of a sealed chamber with an excess of saturated sodium chloride, at saturation, sodium chloride has a water activity of 0.75 as long as the temperature's 25 degrees C. Over time, that cracker, as it's exposed to those conditions of 0.75 water activity inside that chamber, will be forced to absorb, both add and probably absorb moisture until its water activity becomes 0.75, equal to the conditions inside the chamber, at which point it will stop because it's come to equilibrium. And in that process, it will have gone from 4% moisture to 20% moisture content. And of course, the texture is going to become very soft as opposed to the nice stiff initial texture. If we likewise take cheese in a separate container and put it in with saturated sodium chloride, cheese is fresh cheese is a very high water activity product at about 0.90 water activity and about 60% moisture content. When it's exposed to the conditions of 0.75 water activity in a chamber, it will alternatively have to lose moisture to the system in order to come to a water activity 0.75, and will continue to do so until it's reached that 0.75 level. In the process, it will have lost 30% moisture content as it goes to water activity 0.75. So if I were then to take equal amounts of my cracker and my cheese that have equilibrated, and I were to put them together in a sealed chamber in equal amounts with full contact with each other, the question is, which way will water move? Will it move from the 20% cracker to the 30% cheese, the 30% moisture cheese to the 20% moisture cracker, or the alternative is, will water not move at all? And of course the answer is that water will not move, and that's because the water activities of the two materials are exactly the same. Even though their moisture content is very different, their water activities are the same. So the energy of the water in both systems is the same. There is no motivating force because water moves from high energy to low energy, not high concentration to low concentration. So how would you go about using water activity to control powder flow? This is a process that would start all the way from research and development to then looking at income and ingredient inspection as powder ingredients come in, looking at then in-process control to be able to effectively control problems that could happen with powders, then developing a release specification for the powder product, and then all the way to quality assurance, especially if the powder itself is your product and you're producing it as an ingredient to then sell to subsequent manufacturers. The nice thing about water activity is that through all this process, what you can develop is a specification that is the same no matter what location you're at around the country, around the world. You would be able to use one specification for moisture, that being water activity. That means that everybody can then also use the same instrumentation, water activity meter, to be able to track that. All that data can be directly related to safety and quality and even be used to model what the shelf life is going to be of a product, and be able to determine whether or not it's being optimally produced. So let's talk a little bit about this process. So research and development's job would be to use information about the moisture characteristics of the powder, and then use that information to optimize its performance in its flow properties and its quality properties. And then quality assurance would take that specification that's been established by research and development and then use it as a release specification to make sure that the powdered material is being processed to an acceptable water activity level. So the critical information that you would need to be able to start using water activity to control the flow properties of powder is first, you would need to figure out what you can learn from the moisture absorption isotherm to be able to set that moisture content or that water activity release specification. So the next is to determine and know how you would actually measure those moisture absorption characteristics to identify that water activity specification. And then the third thing is how would you then test water activity as a quality assurance tool using the specification that's been established from research and development. So first let's talk about what applications you could use moisture absorption curves for in powders. And you can use these to look at hysteresis, look at how things wet and dry, how to correctly formulate them, physical changes can occur, all the way down to packaging requirements in order to maintain a desired shelf life. So when we take a look at moisture absorption curves, the first thing we need to realize is that the moisture absorption characteristics, that water activity to moisture content relationship, is unique for every type of product, and even unique for each type of powder product. But you can see pictured in the figure that's shown here on the right, these are different types of products, anything from wood pulp up to a cream filling to milk powder. And notice how the shape of the isotherm is very different for each type of material. That shape is dictated by the chemical properties of the matrix and how many water binding sites are present in the matrix. It has an influence on what the shape of that curve is. And notice also that it's not a linear one-to-one relationship, and in fact the shape of it will change for most types of products depending on the water activity range that you're investigating. So we have here a figure that shows what we call a dynamic isotherm. So this is a water activity versus moisture absorption curve that's been generated using a dynamic method that provides these very high data resolution moisture absorption curves, as opposed to what many people are familiar with, which we call the DVS or static method that originated from traditional desiccator method, where you hold at a given humidity level and then track the change. This is done in a dynamic way that I'll explain in just a second. The important thing is that from these dynamic curves you get these very high resolution isotherms, which have very distinct and interesting inflection points that are resulting from drastic changes in absorption properties resulting from changes in the matrix. So for instance, in this case, we see this spray-dried milk powder. It is processed to an amorphous glassy state, as we alluded to earlier, and would stay in a metastable condition as long as it maintained that glassy state. Once it starts to absorb moisture, it can move past what we call critical water activity, highlighted here by the black circle. And notice that it's on the inflection point in that isotherm curve. That inflection point is indicative of a glass transition or phase transition that results in high mobility and the opening up of lots of water binding sites as a result of that causes that drastic change in absorption properties. So using this information, we can now identify where that transition from the glassy state to the rubbery state happens, and we identify that as a critical water activity, which is specific to the temperature at which we do this investigation, in this case at 25 degrees C. So initially all we see is surface absorption until that transition occurs, in which case we now see surface and bulk or adabsorption occurring as a consequence of the phase transition that has occurred, and eventually these particles will wet and will go into solution. Now the question is this a real phenomenon that happens due to the uptake of moisture? And in fact, the transition is repeatable. You can run it multiple times on the same product and you'll essentially get the same isotherm curve. And notice that these dynamic isotherms give us valuable information about what the nature of a powder material is, whether it's crystalline or amorphous. Pictured in the figure that's shown, this is sucrose, same exact chemical formula, just one that's been processed to be amorphous and one that's been processed to be crystalline. Notice the very distinct and different shapes of those isotherm curves. The amorphous sucrose experiences a glass transition indicated by that sharp inflection point in the dynamic curve at a very low water activity. And then once it has gone through that transition, it will become susceptible to caking and clumping. Whereas crystalline amorphous, of course, stays in the crystalline state and experiences this typical J-shaped isotherm that exists for crystalline materials who experience deliquescence. And this deliquescence causes a sharp, distinct 90-degree turn in the in the moisture absorption curve at the critical water activity for deliquescence, which for sucrose in this case is about 0.85. Now, the typical way to be able to investigate glass transition in powdered materials is to use what we call a DSC analysis. So this is a thermal analysis that identifies the glass transition temperature, or TG as it's often referred to, by scanning temperature ranges until it induces some sort of an enthalpy change that's indicative of a glass transition. So in that case, water activity, or more correctly, moisture content, is held constant as the temperature changes until you cross that line. Alternatively, the thing that we're doing with these moisture absorption curves is we're holding temperature constant and then tracking changes in water activity until we experience or induce basically the same change that was induced by temperature. But in this case, we're doing it by moisture instead of temperature. So the idea is that either way, we're getting to the same transition point, whether you do it by temperature thermal scanning or you do it by moisture absorption properties. And here we see pictured that we can identify these glass transition inflection points in the dynamic curve for lots of different types of glassy materials, from milk powder to maltodextrins to infant formula to fiber powders that are primarily fiber materials, and even to protein powders. As they're in that amorphous state and fairly low molecular weight, it's possible to be able to see these inflection points in the curve. Now, if we change the temperature of the isotherm, we will change the critical water activity. And you can see pictured here that as you change from 40 degrees C down to 15 degrees C, the critical water activity as temperature increases goes to a lower water activity. And this is important because at 25 degrees C, you may be sitting at 0.3 water activity for this particular spray-dried milk powder and be below that critical water activity for 25 degrees C. But what if you're increased suddenly to 40 degrees C? The critical water activity then shifts to a lower value at about 0.29, in which case you're now above that critical water activity. You'll experience a phase transition. The powder will experience a phase transition, will suddenly become susceptible to caking and clumping. And water activity and glass transition actually are, as we alluded to earlier, are very well correlated. It's actually quite a linear relationship over the practical range of water activities that you might experience. And so it's possible even to be able to create a correlation where you can determine the glass transition temperature for a particular product at any given water activity. So this RHC, or this critical water activity that you identify from these dynamic moisture absorption curves that would be done using or by research and development, they would use this information to be able to identify this critical water activity. Now this critical water activity becomes the specification or the critical level for this particular product. And so it's important to know what that critical water activity is at the typical storage temperature, and that becomes the water activity specification. So once you've identified what that value is, you would track expected storage temperatures and then figure out what the critical water activity is going to be at worst case scenario storage temperatures. This critical water activity becomes then the water activity release specification. QC tests on the products are done to make sure that it meets that release specification. And then, of course, you package the product in such a way to prevent it from experiencing water activities higher than the critical water activity, even under extreme conditions. And as long as you can do that, then you should be able to maintain the flow properties of that material. Second thing you need to know is how do you actually generate these moisture absorption curves. And there's essentially three different methods for doing this, from the traditional desiccator method to the dynamic vapor absorption method that's typical of instrumentations in the marketplace, and then the new dynamic isotherms that I alluded to earlier. So first, taking a look at the traditional desiccator method, This is the old way of doing isotherms, where you essentially take different sealed containers, and in them you place saturated salt slurries from different salts. Each salt at saturation has its own unique water activity, again dictated by thermodynamics. So you take lithium chloride, put it in one at saturation, it creates a water activity of 0.113 at 25 C. Put saturated sodium chloride in another at saturation, it creates a water activity of 0.75. Take your product, stick it in the containers with an excess of those saturated solutions. Wait, sometimes 2 to 3 weeks for equilibrium. When weight stops changing, you take them out. You know its water activity based on the salt that was used, and then you know its weight change, which can be used to calculate changes in moisture content. So each desiccator essentially gives you one data point. Problem with this, of course, is that it's very labor intensive, very time intensive to be able to get this data. So it's really not a viable method. Thankfully, this process has been automated in what we call the dynamic vapor sorption method, or DVS, where it takes this process that's done in the desiccators and automates that whole process. So inside of a controlled atmosphere chamber, you have a weight or a scale that's tracking weight changes for the material. So you expose it to a given humidity condition, whatever pre-selected value that is, and then the scale tracks the weight change of the product until that weight stops changing by some preset level that triggers and identifies that equilibrium has occurred. And then it would naturally or automatically step up to the next humidity level as it's been set and to repeat the process, so forth and so on, until you get many, many data points for across the moisture absorption curve. So this would be faster than traditional methods because you don't have to have all the labor of taking samples out, tracking their weight, putting them back in. So it speeds up that whole process, facilitates the ability to also look at kinetics absorption, which are telling of the diffusion properties of a particular material provided by these DVS methodologies. Dynamic isotherms, on the other hand, don't rely on equilibration to known water activities to get the water activity level. Instead, what happens with this methodology is that a sample is placed in a chamber and then exposed to either completely saturated wet air or completely desiccated dry air, depending on if it's adsorbing or desorbing. And as that happens, the sample is forced to take up moisture or lose moisture. And as it does so, after a certain amount of time, the airflow will be stopped so that the chamber now is just sealed, no air flowing into it. Will come to equilibrium with the vapor pressure of the sample, and that can then be used to determine water activity directly using the same technology that we use in our water activity instruments. So that we get a water activity value. At the same time, a weight's taken on a precision scale so that the weight change is tracked that's associated with that water activity change. So that's a real data point, and each time that happens, you get a data point. So this is much faster because you don't have the time to wait for equilibration than the traditional static or DVS methodologies. So you can get a full adsorption, desorption isotherm curve for a product in about 24 to 48 hours using this methodology instead of a week to 2 weeks. And you also get these very high data resolution curves that you wouldn't be able to achieve in any logical amount of time using the older DVS method. So you get very fine resolution. Every 0.01 water activity change, you would get a data point. And with these high resolution curves, then you can see these important inflection changes in the isotherm curve that help to identify those critical water activities as we talked about earlier. So if we do a comparison between isotherm methods, we have the traditional desiccator that gives us very few data points and are based upon equilibrium information versus the dynamic method that gives us very fast results and very high data resolution. And notice in this case, for the spray-dried powder, there are big differences between the two, and those differences are very important. With the traditional methodology, we'd never see the inflection point that indicates that critical water activity where the phase transition occurs. You wouldn't be able to investigate that with traditional methods. But without the traditional methods, you also wouldn't be able to go in and look at the kinetics absorption. So both of them provide valuable information that can be helpful for doing observations on stability. And because of that, we've now created from Decagon what we call the Aqualab Vapor Absorption Analyzer, the Aqualab VSA. And this is the only instrument out there to do moisture absorption characteristics that combines both static and dynamic methods in one instrument. In fact, you can even perform them on one sample during a testing process. So this is the only instrument that will do the traditional static methods, does them the same as any other instrument out there, but also offers this dynamic method for being able to investigate these glass transition, phase transition occurrences. And that uses that, to do that, it uses a dynamic method we call DDI, Dynamic Dew Point Isotherm Method, which is a patented method that's controlled by Decagon. So this instrument coming out from Decagon, the Aqualab VSA, is the only instrument out there that can do both static and dynamic in one sample. And this is just an example of what that looks like. Notice here, this is microcrystalline cellulose. It's been analyzed in the Aqualab VSA. Was initially done using static techniques and then followed up using dynamic techniques. You'll notice that there's very good agreement between the two types of curves generated either using DVS or DDI for this particular sample. But also notice the differences in resolution from the two methods. The DVS in this case took about 4 days, 5 days to finish. The DDI took about 2 days in comparison to the resolution that comes from them. And if we take the information generated from a DVS isotherm using our Aqualab VSA and compare it to other DVS instruments that are out there, as well as traditional desiccator methods, you can see that there's very good agreement between the information that's provided from our DVS method to any of the DVS methods out there. It's equivalent. Now, if we have just a system that does dynamic isotherms, of course, you can see these interesting inflection points that indicate glass transition and where the critical water activity is, but it doesn't allow you to visualize crystallization, which can happen for powders once they've gone through glass transition. And it also doesn't allow you to do any kinetics absorption. So it provides valuable information, but not necessarily all the information that you might want. If you only have static isotherms that come from DVS, typical DVS instruments, of course you'll get your isotherm curve, but it's very limited data resolution. As such, you won't be able to see that critical inflection point to identify the critical water activity. But you do get to visualize crystallization, where you see a distinct drop in the isotherm curve due to the crystallization process and pushing water out. And you also get these nice profiles, the kinetic profiles that allow you to do comparisons between diffusion properties of different products at different water activities. So ultimately, the best type of instrument would be able to, again, combine both static and dynamic in one instrument and even on one sample, as indicated here. We run both on this spray-dried milk powder. Using the dynamic method first, we can see that inflection point that indicates the glass transition because of the high resolution. Switch over to the static method where we're held till equilibrium. Now we've slowed everything down. There's enough time for crystallization to occur. And you see the distinct drop in the isotherm curve indicating crystallization. And then you see the limited data resolution, but you're also getting that kinetics absorption information once you've switched over to the DVS methodology. So the third thing you'd need to do in order to be able to incorporate water activity as a methodology for being able to control flow properties of powder products or ingredients is to know how to measure water activity. And this would be done again by a QC person who was checking either the incoming powder ingredient, or if you're manufacturing the powder material, then the outgoing product that's headed to a manufacturer. The QC would use it's a very simple instrument, uses a dew point technology. By knowing the dew point of headspace, you can determine exactly what the vapor pressure is. That's the numerator. And then from the sample's temperature, you can figure out and calculate the saturated vapor pressure. You divide the one by the other. The ratio is the water activity, and that provides that information. Very fast, 4 to 5 minute test time, a very high level of accuracy, very good repeatability. So it's a very simple process to be able to measure water activity. Once you've established what the critical water activity is, the process of then measuring water activity is very simple. And here's an example of what a water activity instrument would look like. It's a clamshell design, making it easier to access the interior and clean if needed. And sample goes in, sample comes out, sample goes in, close the lid, push the lever over, takes a measurement, reports water activity temperature, open it up, put the next sample in, close it, push the lever over, does the next water activity. Very, very simple to use. But there are some features on this that are helpful. It has onboard storage, so it will store your results that you can then later download to a computer using a software program that we offer. It has administrator settings to lock people out if you so choose. Has a volatiles option, which typically isn't a problem in powdered materials, but if something does interfere with the mirror, there's alternatives to be able to still measure water activity. So very simple instrument. Once you've established that water activity specification, to go to then measuring water activity is a fairly simple process. It just requires purchasing an instrument. And here you see a comparison of the performance of the Aqualab water activity instruments on different types of standards. Very, very high level of accuracy across the water activity range. These are very reliable and easy to use instruments. So what do you need to know to be able to look and predict the shelf life of powders? Understanding that this transition to the glassy state is important, and you know you need to keep your water activity levels below that. Once it's moved above that critical water activity, it's just a matter of time. Even below those levels, it's still a matter of time. It's just that the time is extended out to years as opposed to weeks or months when you move past the glass transition. But ultimately, what you need to know is the water activity, the temperature, and the time. And if you know that information and you've generated it or collected it for different types of powders and tracked exactly how long under those conditions does it take for caking and clumping to occur, then as long as you know the conditions that your product has experienced over time, it's possible to create a model that will allow you to determine what its current shelf life is based on the conditions that it experience. This is something new that we're developing here at Decagon. We call hydrothermal time, but has the potential to be very valuable in being able to track the shelf life of not only powders but all types of products. And ultimately what you need here is good science and not guessing. If you explore and investigate these powdered products, it's possible to get a very clear idea of what it is that's influencing the caking and clumping. Even though you may not get the specifics of what is going on internally that causes or leads to it, it's possible to get these more macroscopic external measurements that have good correlations that can then be used for specifications and to be able to control stability, such as water activity. So how do you begin using water activity to control powder flow? First thing to do from a research and development standpoint is to do a moisture absorption isotherm curve. The options here are that we offer an isotherm service here at Decagon, where we provide isotherms for different products. You just have to call in and ask us about that. It's a fee for service. We also, of course, sell the Aqualab VSA so that you have it in your own facility and you can run as many samples as you want, with the idea of investigating these specific characteristics of the powders and identifying where those critical points are. Once you've done that, then that allows you to establish a specification. And then you base that specification on worst case scenario conditions, also on packaging. Packaging, of course, is something we didn't specifically talk about, but it certainly plays a role in all of this because it ultimately is what's going to determine how quickly the water activity of a powder material changes when exposed to different conditions. But you measure the water activity of the product after it's manufactured using the easy-to-use water activity instrument in a QA/QC setting. Make sure that it's below the specification that's been set for stability. Once you've been able to figure that out, then you can go forward using that specification to track the stability of powders. And the key here is that this methodology, or this proposed methodology, it involves easy-to-use instrumentation, but it delivers incredibly powerful science that will allow a person to be able to gain better control over the stability properties of their powder material. And with that, I thank you and hope that this was informative.